Hi, today we are going to talk about queuing systems that have only one server. We call these systems usually MM1, which means we are assuming that the inputs are or arrivals, the time between arrivals is exponentially distributed, the service time is exponentially distributed, and there is one server, and we have infinite capacity. So this is infinite. The population, this is a general discipline, infinite capacity, and the population these arrivals are coming from is also infinite. So the system, the rate diagram for the system is going to look like from previous lectures. We know that these states are the number of customers in the system. 1, 2, 3, 4, and so forth, and this keep going. There is no capacity on the system. The incoming rate is always lambda, and because there is only one server, this is mu, mu, mu. So these are some assumptions that um, we have for this type of systems. First, we are assuming that infinite arrival population, this last letter here, last character, and these arrivals are independent. For example, the third customer, arrival of the third customer does not have any impact on the arrival time of the fourth customer or any other one. And the next assumption says that the arrival process is Poisson with an expected arrival rate of lambda, memoryless. And also it's independent from the number of customers in the system, which means if you see that there's a long line, you're not gonna avoid. This is not a system where arrivals are avoid joining the system because there is a long line. And the queue configuration is single queue with possible infinite, theoretically infinite. So there are people waiting in line, people keep adding, can keep adding, and then there is one server. So there is one line here. And then people will not leave the line, and also people will not join. We won't have more than one arrival in any given point in time. The Q discipline is general discipline, which means the formulas that we're going to develop work for any type of uh, discipline, Q discipline. First come, first serve, random, and all of those things that we learned about. The service mechanism consists of a single server with exponentially distributed service time, which is the second M here, notice. So we're going to work with mu and lambda. And then there are some metrics that we're going to develop for an MM1 that has a mu and lambda as its rates. The first one is the average number of customers present in the system. Average number of customers waiting in line, Q stands for Q. Average number of customers in service. W, average time a customer spends in the system, average time a customer spends in line, and average time a customer spends in service. So here you see that these three are talking about time, these three are talking about number, and these are just rates. And we already learned a few other things, which were the pi's, pi sub j, which means the fraction of time there are j people in the system, including in line and being served. So, um, so these values, these variables, L's and W's and pi's, these are the values with which we characterize a system, a queuing system. So one thing that we're going to use in our formulations and in our formulas is called rho traffic density, lambda over mu, and we want that to be less than 1. If it's greater than 1, we would say the system blows up, which means it never reaches a steady state. The size of the line keeps growing and growing and growing until the system never reaches a steady state. never settles down, never reaches the equilibrium state. Um, Therefore, um, we won't be able to study a system if this rho is greater or equal to 1. How do we make it less than 1? For example, you may hire a server that's faster. You may add assistants to the server to make it faster so that lambda is increased, the number of people you serve per time unit increases, sorry, mu increases, and then lambda over mu becomes smaller, hopefully less than 1. All right, if we have rho, our pi naught, pi 0 is going to be 1 minus rho. And pi j's are going to be rho to the power of j times 1 minus rho. So this is basically pi 0, and this is our CJ that we learned in birth, death processes. So CJ for MM1 is just rho to the power of j. C2 is, for example, lambda over mu to the power of 2. All right, so now I'm going to show you how we develop these formulas. Everything you see here is to just show you how we get there, but what you need is what we will see at the end in that circle. So first, this is basically the formula that we just had. Pi j equals rho to the power of j times pi 0. Rho to the power of j times 1 minus rho. Okay. And we also know that sum of these pi's is 1. And I substitute each pi with this. And then I factor pi 0. And I name this part S. So this part, I call it S. And if that is S, if I multiply each side of this by rho, I can see that S rho is equal to, because this becomes basically I factor rho again, S minus S rho becomes 1, and then I factor S, and here you see that S is 1 over rho. I'm going to use that. I'm going to use that somewhere. So pi 0 times S, or 1 over rho, is 1, right? Why is that? I'm basically rewriting this term here. I'm rewriting this. Pi 0 times S. What is S? S is 1 over 1 minus rho. We just showed that. If that's the case, pi 0 is going to be 1 minus rho. That's how we developed it. And then we learned that pi j is just rho to the power of j times 1 minus rho. Okay, now we're trying to find, so we got the pi's. Now we're trying to find L sub Q, L sub S. So here you see that first we want to make sure that rho is less than 1. If rho is not less than 1, we won't be able to calculate L. What is L? Expected number of people waiting in line. Okay, whenever we say expected number, it means outcome times probability. Expected value in general is each possible outcome, summation of each possible outcome times its probability. For example, expected value of X is summation of I goes to N. That's 1 to N. Let's assume that X can take N different values. And PI, probability of X assuming Xi value. X of I is one of the values that X can take. So when I say what is the expected number of people in the system, number of people in the system is Xi's, can be 0, 1, 2, 3, 4, and so forth, right? And let's see what is the probability of that. Probability of that is just pi's, right? Remember pi sub j was the probability that there are j people in the system, or fraction of time that there are j number of people in the system. And these are possible values for the number of people in the system. So the expected value is going to be 0 times its probability, 1 times its probability, 2 times its probability, and so forth. So let's do that. L is j times pi sub j. And we just learned that pi sub j is rho j times 1 minus rho. And if we factor 1 minus rho, we're going to get that term. And that's a series that can be reduced to this is the same as this. And from here, these two cancel out. This cancels out with this. Here you see that L becomes rho over 1 minus rho, or lambda over mu minus lambda. So if, for example, a system has a lambda equal 3, mu equals 5. 3 people on average arrive every minute, and 5 people can be served every minute. That's the rate on average. So my rho is going to be 3 over 5, or 0.6, and therefore L is 0.6 over 1 minus 0.6.4, which is 1.5. So on average, there are 1.5 people in the system, including inline and being served, for that lambda and mu. All right, next I'm going to calculate LS, number of people being served. Okay, how many people can be served in the system? Like, what are the possible values that L sub S can take? As you can see, number of people. So this first line is the possible number of people in the system. If you have no one in the system, no one is being served. And if you have one person in the system, that one person is being served. And if you have more than one person, 2, 3, 4, j, only one of them can be served, right? So these are the possible values for L sub S. It's either 0 or 1. What's the probability of 0? Pi 0. What's the probability of 1? 1 minus pi 0, basically pi 1 plus pi 2, and so forth. Therefore, L sub S is going to be 0 times pi 0 plus 1 times some of the other ones. And we know that this is 1 minus pi 0. 1 minus, what is pi 0? This is pi 0. And that becomes just rho. And what is rho? We know that it's lambda over mu. So we learned that L was rho over 1 minus rho, and now we learned that L sub S, expected number of people in service, is just rho. Next, I'm going to calculate expected number of people waiting in line. Because there is just one server, or let's say that this way. Because total number of people in system, L, is composed of total number of people waiting in line and total number of people being served, therefore L sub Q is just L minus L sub S. And we already calculated both of those. So I can say that L sub Q is L minus L sub S, and I get this value. All right, I got all the L's, all the expected numbers. So for example, for a system whose mu is 4 with a lambda of 2, rho is 0.5, L sub Q is 0.5 to the power of 2 over 1 minus 0.5, which is 0.5. On average, there is half a person waiting in line. Or on average, half of the time, there is only one person in the line. Half of the time, no one's in the line waiting for that system, which means it's an efficient system. There, you won't be seeing a lot of people waiting in line. That's just another form of writing rho squared over 1 minus rho. Now, to calculate W's, which is the expected time the customer spends in line or being served or spends in the system, we have this beautiful formula which calls the Little's queuing formula, L equals lambda times W. How do we use that? It's basically dividing your L by lambda to get the W. So here you see that W is L over lambda. So whatever formula we had for L, we just divide that by lambda to get W. W expected time a customer spends in the system is just L over lambda. W sub Q is L sub Q divided by lambda, and WS is L sub S divided by lambda. Okay, so this is a summary of everything we saw so far. We define rho first. We want to make sure that it's less than 1. Pi 0 is going to be 1 minus rho. Pi sub j is rho to the power of j times 1 minus rho. L, expected number of people waiting in line. Expected number of people in the system, including waiting in line and in service. Expected number of people is lambda over mu minus lambda. L sub q is lambda squared over mu times mu minus lambda. L sub s, expected number of people being served, is just rho, or lambda over mu. Therefore, W is going to be, because it's L over lambda, it's going to be 1 over mu minus lambda. W sub q is going to be lambda over mu times mu minus lambda, and W sub s is going to be just 1 over mu, using the little queuing formula. So now let's look at an example. Think of a drive-through bank, and here is the problem description, and we will be answering those questions. An average of 10 cars per hour arrive at a single server drive-through teller. Assume that, so this 10 cars per hour is going to be my lambda. Assume that the average service time for each customer is 4 minutes. So 60 over that is going to be my mu. And both inter-arrival times and service times are exponential. That's MM, and there is one server because there is one teller. Answer these questions. What is the probability that the teller is idle? So my mu is going to be 60 over 4, 15 cars. As you can see, lambda over mu is going to be less than 1, so we're okay. So the server is idle when there are no customers in the system. What fraction of time, or what's the probability that there are no customers in the system, no cars in the bank, at the bank? It's just pi 0. And then what is the average number of cars waiting in line for the teller? Because it's asking about number, that gives me the hint that I should be calculating L. Waiting in line, therefore it's going to be L sub Q. What is the average amount of time? So this is one of the W's. A driving customer spends around the bank's building, including the time in service. So in general, how much time a car spends in the system? In general, the whole system, so that's just W. And finally, on average, how many customers per hour will be served by the teller? You may think, well, that's mu, but mu is the capability. So mu is capability, which means the server can serve 15 cars per hour. But how many do they actually serve? That's mu times fraction of time that the server is working. What's the fraction of time that the server is working? Is 1 minus pi 0. Now let's calculate all of this. Queuing system, it's MM1, and lambda is 10 cars, mu was 15 per hour. Note that these are all per hour. And then rho is 2 over 3, less than 1, check. What is the probability that the teller is idle? So pi 0 is 1 minus rho, 1 minus 2/3, 1/3. 1/3 of the time, the teller is idle, it's not working. What's the average number of cars waiting in line for the teller? So L sub Q. We had a formula we just developed for L sub Q, rho squared over 1 minus rho, and rho was 2/3. Just substitute rho with 2/3, and we get 4 over 3 customers. A bit greater than 1.3 customers. What is the average amount of time a driving customer spends in the bank parking lot? So we learned that W is just L over lambda. So L is 2 customers, W is going to be L over lambda 2 over 10, which is 1/5 or 12 minutes. And then there was a question, on the average, how many customers per hour will be served by the teller? 1 minus rho 0, 1 minus 1/3 times mu, which is 15, 10. So although they are capable of serving 15 people, 15 cars per hour, actually, on average, they serve only 10 cars per hour.